Good morning, everyone. I'm Francesco Decataldo, a PhD student in physics in the University of Bologna. Thank you, Tobias, for the kind introduction. Today I will talk about my work on stretchable and low-impedance polymer-coated microelectrodes for peripheral nerve recordings. Neural interfaces are gaining much interest in these last years due to the possibility to monitor and record nerve activity in order to get a good understanding of how the nervous system controls our body function. But moreover, bioelectronics aims at stimulating, thus exploring basically new electroceutical instead of pharmaceutical or chemical treatments in order to cure diseases or restore some functions. In particular, stimulation and recording of autonomic peripheral nerve is quite important due to the fact that they are correlated to numerous and several inflammations, and also are the mediator that the brain uses to keep our physiological homeostasis. Standard acute and chronic recordings are done thanks to stiff metallic inorganic electrodes that are clamped to the nerve itself, but this has many drawbacks because it causes bleeding at the insertion site and inflammation for long-term recording due to the invasiveness of the electrode itself. Moreover, they have relatively high impedances and poor bioconformability with the nerve strand. Thus, a suitable and alternative way to bridge the gap between the nervous system and the inorganic electronic devices is the use of conductive polymers as neural interfaces, and in particular we employed PDOT-PSS due to its wide range of properties. It is indeed a wide range of conductivity according to the doping. Low impedances once deposited in thin films. It is able to conduct both ions and electrode, and it is more biocompatible and more soft compared to its inorganic counterpart. Here is the device configuration. It is based on two metallic stripes that are encapsulated in two PDMS layers, leaving an open trench of 400 micrometer wide for the coating of the electrode that are coated with PDOT-PSS PEG. We introduced the PEG as a plasticizer in order to improve the elasticity of our electrodes, and here you can see the uncoated and the coated electrode optical images together with a picture of our electrode that is basically the dimension of the tip of a finger. Here are the fabrication procedure that is based on several steps, but is quite an easy procedure that can be done outside of a clean room, fabricating tens of electrodes in 3 to 4 days. And the last step is an evaporation of titanium gold on the bottom of our electrode in order to shield the signal from external noise. In particular, an important step of the fabrication is the electrodeposition of PDOT-PSS PEG. We use an electrochemical deposition starting from PSS, ADOT, and PEG molecules in a water solvent, and we introduce two improvements. We did a thickness control deposition in an inert atmosphere. Thus, in this case, we flux nitrogen in order to avoid the oxygen-related termination of the PDOT chain that could lead to shorter chain and thus to an easier delamination of the polymer. We indeed fix the thickness of our polymer with a chronoamperometric deposition, fixing the voltage at 1.2 volt and then integrating the current, thus calculating the charge that we are depositing and fixing the charge amount that we want to deposit, thus the thickness of the electrode once we know the area we are depositing on. We then studied the presence of the PEG inside of our polymeric mixture, and what we did is to use the Fourier transform infrared spectroscopy, and as one can see from the green arrow, basically there are CO stretching vibration bands at 1108 centimeter of the power of -1, together with CC fingerprints that basically state the presence of the PEG in our mixture. And these prints, basically this spectra, is kept even after 2 weeks of immersion of our electrode in PBS. Thus the PEG molecules doesn't leak out from our polymer. Here it is presented the impedance of our electrode before and after the coatings with the two different polymer. In particular, we use an RC circuit in series to model the system. The R stands for the electrolyte resistance for the flat response at high frequency, while the C is for the ionic double layer at the low frequency of the spectra, and we basically, depositing the p dot, we basically move from a two-dimensional metallic interface to a three-dimensional polymeric one, thus enabling also the ionic conductivity in our electrode. And in this case, this is translated in the impedance with a low down of the impedance and also an enhancement of the flat area of the response of the electrode, in particular in the area between 100 Hz and 3 kHz that is interesting for bioelectronic recordings. With the addition of PEG, the curve is almost the same. We had just a reduce of the value of the capacitance per unit area. Okay. Our FM is able to couple a morphology investigation of our film together with an electrochemical spectroscopy using the film as a working electrode. And in this case, all is done in liquid because we need to understand the properties of the polymer in liquid that changes due to the swelling, due to the uptaking of water in the polymer that changes its thickness from one end and also becomes software for the water uptaking. We studied the morphology of P.PSS and P.PSS PEG, and fitting the 8-to-8 correlation function, what we obtain is that roughness and autocorrelation length basically reduce when we introduce the PEG in our mixture. And in particular for P.PSS, we have the roughness and correlation length that are increasing for increasing thickness, and the P.PSS show the typical cauliflower structure. On the other end, for P.PSS PEG, this behavior is no more present, and we have almost a constant value for the two parameter, and indeed we have also smaller structures in the film itself, probably due to an altered growth mechanism during the deposition. But we want to move from the macroscopic study of the properties of our electrode to the microscopic one that could be different, and in order to do that, we move from the typical tensile strain experiment to a nanodentation experiment using the AFM to indent our polymer thickness, our polymer, in order to understand its micromechanical properties, thus the one that the nerve itself experiences during the implant. And we see that with the gold addition, we have an increase of the Young modulus going to 32 megapascal, but once we add the polymer P.PSS, and in particular the polymer with the plasticizer, this Young modulus reduces to 14 megapascal, thus being more conformable and more mechanically compatible with the neural tissue. The important property of the PEG can be understood when we study the electrochemical impedance of our system under strain. Indeed, for a standard gold electrode, what we see is that the impedance is more or less constant during the strain up to a value of 60%, because gold basically form micro-cracked patterns that are still able to conduct between the different gold highland. While when we introduce the P.PSS, huge crack starts to form and there is a steep increase of the impedance at 10% and we lose the contact at 20% of strain. In order to keep both the low impedance of the polymer together with a good stretchability, we introduced the PEG, the plasticizer, being able to have a almost constant value of the impedance up to 40% of strain. In order to understand this behavior, we performed an AFM measurement using under strain, thus using a mechanical order that was able to keep the strain of our polymer while we perform AFM images, as done in a previous work of the Professor Kramer shown on the right. And what we saw is basically that a comparison between gold and P.PSS show that the micro-cracked pattern of gold is quite different from the huge crack that forms in the P.PSS coated one, seen both optically and also with AFM images. While the behavior of gold and P.PSS PEG is almost the same with a micro-pattern crack. But how to understand this? Starting from the situation without any strain, we can see that basically there are the surface height modifications that could be seen in all three of the images, and are probably due to the gold layer underneath the micro-cracked gold layer. In this case, when we introduce the strain, the gold basically start to form cracks that are orthogonal to the strain but are still few micrometers. But this is not what happened when we have P dot on top of gold, and in this case we add additional forces during the crack formation. Thus we have fewer cracks but they are wider, and this basically cut the conductivity of our electrode. This doesn't happen when we have a plasticizer like PEG, and again, the micro pattern of microcracks is restored. In order to test our devices, we did a chronic recording. We implanted on the renal nerve of rat, and we did a chronic recording using a system of a telemetry system that was placed subcutaneously to the rat, together with blood pressure monitoring, always with the telemetry system. In this case, this is the implant, and we placed the trench below the nerve strand, and then we sealed it with silicone in order to keep the electrode stable. After the surgery, we started the chronic recordings, and this is a typical trace after 14 days from the surgery, and this is basically the blood pressure, the heartbeat that are almost constant, and the renal sympathetic nerve activity in time. Okay. Zooming on this graph, what we saw is basically that our renal activity is synchronous with the cardiac rhythmicity, and this is a typical behavior of sympathetic nerve, such as renal nerves, splanchnic nerve. Thus, basically, we have bursts of tens of microvolt, where we have the diastolic blood pressure, while for the systolic peak there is the inhibition of our signal, and there is just a thermal noise due to the amplifier. So this is a signal of good quality of our recordings. In particular, we didn't show any ECG or EMG that were shielded by the ground contact that we put on the bottom of our electrodes. So to conclude, we managed to realize elastic bipolar electrode in order to achieve a good signal of the nerve activity in long-term recording. And in particular, we had the PEG plasticizer in order to improve the elasticity of our PSS low-impedance electrode. Finally, AFM measurements were performed on stretched thin films in liquid in order to mimic the biological implant itself. And this allowed us to say that basically with the PEG, we have an altered growth mechanism that lead to a lower Young modulus and a more elastic film. I would finally like to thank all the people that allow me to do this work. So starting from my department, the physics department where I'm currently working, and also our collaborators at the Department of Biochemical and Neuromotor Science, the Department of Industrial Chemistry, and the Fleury Institute of Neuroscience and Mental Health, together with the CNR Yes Men here in Bologna. Moreover, the DSI that provided us with the system of telemetry, and our fundings of the nanoscience foundry and fine analysis. And thank to all of you for your kind attention.